Welcome students, and today's class we are going to talk about the wave equation in a higher dimension, right? So wave equation so essentially we want to find out a formula for a wave equation, right? So let me write down the problem. We are supposing, so let n is greater than 2 and m is greater than 2. Okay, so we have two numbers m and n which are all greater than equal to, and the function u is in Cm, clear, of Rn cross close 0 infinity. So you have a function u which is m times infinitely differentiable, sorry, not infinitely differentiable, m times continuously differentiable. Okay, so this solves the initial value problem. What is the initial value problem? Utt minus Laplacian of u, this is 0 in Rn cross 0 infinity, clear. U is equals to g and ut is equals to h on Rn cross t equals to 0, clear. Why it is called initial value problem? Because I do not have any information on the boundary or anything. I just know that initially at the point t equals to 0 what u and u with respect to t does. What is our aim? Our aim is to find a formula. Okay, so let us assume that if there is a u which solves this problem, let's call this problem as the 1. Okay, if there is a u which solves this problem, our aim is to find an explicit formula, okay, for u in terms of g and h, clear. So I have to find an explicit formula just like we did in D'Alembert's type kind of formula. You remember D'Alembert's, right? But that is for n equals to 1, clear, the one dimensional wave equation. Here this is an n-dimensional wave equation. Okay, to do that what we are going to do is this. See, we are going to somehow utilize D'Alembert's, okay, but that will be come later. First what we are going to do is somehow reduce this 1 to more or less, how can I put it, like a one, here the wave equation is a little complicated thing for an odd dimension n. So n here, this n, this is the dimension, right? So for odd dimension what we are going to do is we will show that we will deduce something called a Euler-Poisson-Darboux equation. Okay, and that equation in the odd dimension we can convert it to one dimensional wave equation, clear. Okay, and then we'll see how to deal with even dimension, clear. So what we are trying to do here is this. See, first thing first, we want to define a new function using this small u. We want to define a new function. Okay, so the plan is something like this. You see, using small u, okay, we define a new function. Okay, and that function will satisfy some particular equation which we are going to call a Euler-Poisson-Darboux equation. Okay, right. Now this Euler-Poisson-Darboux equation, we can show that this can be converted into a 1D wave equation, clear, equation for n odd. So let's say n equals to 3 or 5, we can do that. Now once we do, after we do that odd, from there via a trick we'll look at it. will solve the wave equation. So basically the n equals to even case. Clear? N equals to even case. Okay. So let us write, try to do that. So what the idea is this? See, the idea is to study the average. Okay. So basically we will define something like this. So let me define for a fixed x in Rn. Okay, you fix a x in Rn, t positive, r positive. Okay, you define capital U of x, r, comma t. This is defined as the average. See, U is given to us, right? I am assuming that we have a U and I want to write U in terms of F and H. Is it clear? Okay, so I am going to use small u. Small u is given to us. So capital U I am defining. This is XR U of YT. Okay, ds of y. So let me clarify what I meant by all of this. What I meant is I am basically looking at the average of u. Okay, so basically how am I defining the function? See, the function here, here x is not moving, right? It's kind of a fixed x. So once you fix a x in Rn, so you fix a x in Rn, so basically your domain will look like this, no? In one dimension, let's just assume how it looks like. Let's say that's your t variable and that's your x variable. In one dimension, you fix a x, okay, and then you look at a ball with center x. The boundary of a ball with center x and radius r. Okay, so you look at a ball something like this. Okay, yeah, of course it should not contain something like this. You look at u for that fixed t. Okay, for a fixed t, see, essentially what is happening is this: for one fixed t, x and r, you define it like this. So you define a u which will be the average of u over that sphere. Okay, now what happens is when you change r and t, so basically now if you define it like this, you can think of this as a function of r and t. Given a x, you can think of this as a function of r and t. So if you change t, you see this will change because u will change and then the average will change, right? And of course with r also this will change. Clear? So for one fix, so basically what we are doing, we are fixing a x, and for that we have two variable function. One is a function of r, one is a function of t. Clear? Something like this. Okay, so we are fixing a x in Rn. Please let me again emphasize here, this is very important for you to understand what I am doing. I am defining a new function of r and function of t. How? This small u I already know, right? So u, I am writing it as an average. Okay, so capital U is the average of small u over the sphere del B. Yes, and now you can think of this for a given x, right? So you see, this will be a function of r and t, right? Of course, because when you change, see, if x is fixed, when you change r, this changes because the radius changes. So basically, the function, the average will change. Okay, it depends on the radius. That's all. It may not change, and the same goes for t also, right? Okay. So what is it? So basically, this is the average of u t. Okay, this is a for fixed x over the sphere del b xr. Clear? So this should be very clear. For a fixed x, I am defining the average. Okay, with using the small u. I am defining a new function capital U using a small u. Okay, and similarly I can also define similarly. Okay, of course I will define g of xr, which is the average of small g y ds y. Here this is a function of r only, because you know there is no t, it's basically t equals to 0 in this case, and h of xr equals to average of del b xr, okay, h of y ds y. Clear? So g and h looks like this. Now so you understand that for a fixed x we regard capital U as a function of r and t, okay, and once you do that you find a new formula, the equation, so equation which U satisfies, okay. So basically let me write down, this is a theorem. This theorem is called the Euler-Poisson-Darboux equation. Okay, what it says? It said that you fix a x in Rn. Okay, fix a x in Rn and let U, okay, it satisfy utt minus Laplacian of u. This is equals to 0 in Rn cross 0 infinity, okay, and u is g, ut is h on the base on Rn cross t equals to 0. Clear? So if you have for a fixed x and the you fix a x and you let that u satisfies this equation. Clear? If it does, then capital U, if you define capital U, so essentially let's call this thing as 2. Okay, 1 I already wrote, there was no need of writing it. So capital U, okay, so then capital U, okay, defined by 2 belongs to, as I told you, it's for a fixed x, yes. So the capital U, which is the average of small u over the ball del b xr, over the sphere del b xr, okay, that belongs to Cm. Clear? Cm, mth times differentiable of Rc. Okay, what sort of function is capital U? See, capital U for a fixed x is function of r and t. R varies between 0 because r is a radius kind of thing, right? So it varies between 0 and infinity, and t varies between close 0 infinity. Okay, so this is in r plus the bar of that, so 0 infinity times 0 infinity. Clear? Okay, and it solves this equation. See, once, so capital U belongs to Cm, so this is m times differentiable function. Of course, why this is m I am saying, because this u, okay, this u, if you remember, we have assumed that this u is in Cm. Okay, this is very important. See, since that capital small u is in Cm, that regularity is getting carried forward here in capital U also. And what you can do is you have capital U of t minus capital U of r minus n minus 1 by r u r, this is 0. Clear? So that is in r plus cross 0 infinity, okay, and capital U is equals to g, capital U with respect to t is equals to h on r plus times t equals to 0. So See, a beautiful thing is happening here. What we are doing here, so this method is called, I forgot to tell you this thing. So this method, what we are going to do, this is called the spherical means. So basically, we are kind of taking a average of a spheres, okay? So see this function 2 which you have defined, which we defined it like this. There is a very beautiful thing about this function. U solves the wave equation, that's for sure. That is given to us, right? And what we are saying is this: the average of U, if you are taking, which you are defining it as capital U, that capital U also satisfies a very similar thing. It's a wave equation, right? If you look at it properly, you see what is this part, capital URR minus n minus 1 by r UR. If you recall, that is basically the radial part of the Laplacian. We did this thing, yes, when we started. So note URR minus n minus 1 by r UR represents the, what does it represent? It represents the radial part of Laplacian. Okay, not part, this is the radial form of Laplacian. Let me put it this way, radial form of Laplacian. Okay, if you remember a Laplacian equation, when we studied the fundamental solution, what did we do? We were trying to look for a radial function, we satisfy the equation, and then we got something like this. Clear? So it is that part. So essentially this is a kind of a radial form, radial with respect to x, utt minus Laplacian u equals to 0, capital U of course. Okay, and this part is the radial part of Laplacian. Okay, so it is in this sense. So essentially this is kind of a wave equation. Okay, so this equation, let's call it 1, 2, 3. Okay, so 1, 2, 3, this equation, let's call it A, B. So 3 is called, I am not writing all the time, you guys already understood, this is this, it's called a Euler-Poisson-Darboux equation. Okay, Euler-Poisson-Darboux equation, EPD equation, clear? Right. So this is after 3 French mathematicians, Euler, Poisson and Darboux. Okay, so let us proceed with the proof of the theorem. So the wave equation is extremely, so before I proceed with the proof of this theorem, let me tell you a small thing without writing anything. Okay, please just listen to this part. Laplace equation, as I already told you, Laplace and heat equations are kind of, very similar kind of behavior. Yeah, they are very much related. Wave equation has a totally different, very independent kind of, they are not, wave equation is not like, the others. Yes, and although it looks very much like a Laplace equation, wave equations are very difficult in general to study. Not wave equation, essentially any hyperbolic equation is very difficult to study. Clear? So for that we are going to do all this. So you do realize that I am in the sphere, I am in the, we are only doing the homogeneous part right now. Okay, and that is why we have to do so many things. More will come. Okay, but that is this for just for the homogeneous part. Okay? So you realize that this is difficult. So let's look at the proof of this. Okay, so before we go on again with the proof, let me tell you what we are doing. First of all, we started with, so we wanted to prove the homogeneous wave equation, initial value homogeneous wave equation. Okay, so let me put it this way: initial value homogeneous wave equation. Okay, we want to prove this. For that, what we did is, first of all, for n equals to 1, we did the D'Alembert's formula. Okay, and after that, what we are doing right now is we are using spherical means, right? Spherical means, what we are going to do with the with the help of spherical means, we are going to reduce something called a Euler-Poisson-Darboux equation. Clear? Once we do this, then using that Euler-Poisson-Darboux equation for n odd, so let's say n equals to 3 or something, we will reduce it to one-dimensional wave equation, solve it, and then write down the problem for n equals to odd. Okay, and then using a special technique, this will define later. Okay, technique. It's not very special technique, but yeah, okay, fine. We'll talk about it later. So once we do that, then we'll talk about n even. Okay, so you realize that this is not a very straightforward thing to do. Okay, so let's look at the proof of the theorem first. First thing first. So for R positive, okay, R positive. Let's look at this thing U, capital U of x r t. So x is fixed, that is why I am just putting a semicolon here, r comma t. This is given by what is it? Yeah, it is integral del b x r, okay, as small u yt dsy. Clear? This is given to you. Now you see, t is not doing anything here, right? I just want to find what urr is, right, for now. Okay, so I want to calculate what u with respect to r is. So you see, but this integral is dependent on r. You remember this sort of integral we did in Laplace equation, right? Mean value theorem while proving. So what we did a change of variable and shifted this thing to the origin. Okay, so this became independent of r, and then we took the derivative with respect to r. Clear? You remember? So we are going to do the exact same thing here. So this is 1 by n alpha n r power n minus 1. Okay, if you just write down the average here, okay, alpha n is the volume of the unit sphere, right? Okay, so this times del b 0 1, if you write it like this, u of x plus rz at t dsz. Okay, I am not explaining every single details, because we already did this calculation. Okay, exact same calculation. So there is nothing, I'm still doing this, breaking the whole thing up, but you guys already know, right? It's just a change of variable. I'm just changing this boundary to the unit boundary. Okay, once I do this, there is the r power n minus 1 here. Okay, now this r power n minus 1, that r power n minus 1 is getting cancelled. So I will be left out with this n alpha n integral over del b 0 1. Okay, u of x plus rz. Okay, u of x plus rz and at t. Okay, and ds of z. Clear? This is what we have. Yes. Now, therefore, what is ur of x rt? What is it? This is given by 1 by n alpha n, okay, integral del b 0 1. So I can take the derivative inside. If I take it, I can use chain rule. I can write it as gradient of u evaluated at the point rz times t, at the point time t, dot the derivative of this thing, which will give you the vector z, and then I have ds of z. Clear? Okay, now again, if I convert it back to the del b xr case, what is going to happen is, let me write it down. Yeah, okay, you can figure it out yourself. So this is the average over xr, okay, del u del gamma of yt dsy. Okay, and this is equals to this is equals to del u del gamma dsy. You remember this formula, right? This formula is essentially by Gauss divergence theorem. Okay, it is r by n will come out because of that average thing, b of xr Laplacian of u yt dy. I hope this calculation is clear. Break it up, then integral of u del gamma at the yt of this particular thing is basically Laplacian of u. That is the definition of that is by Gauss divergence theorem. Clear? Okay, so ur will look like this. Now, of course, this is true. You see that if you put this is for r greater than 0, right? Now as r tends to 0, okay, ur of x r comma t, where do you think this converges? Of course, by looking at it, you do realize that that converges to, you see, that converges to 0. Clear? That converges to 0. Okay. Okay. Since u is in Cm, okay, so it's a continuously differentiable, it's twice continuous, so Laplacian u is in Cm minus 2, okay. So basically it's a continuous function on a ball, okay, boundedness is there for that particular, for this particular term, boundedness is there, okay, for this term, and then r goes to 0, so basically the whole thing goes to 0, okay. Now again, let's do another calculation here. URR of x r t. Okay, let's do that. So what is it? This calculation is so I want to calculate this thing. Yeah, I want to calculate this thing. How do I calculate it? So for doing that, what I am doing is this. See, I will UR is r by n, the average of this, right? So I will break this up and write it like this. See, this is what I need to find. What is URR? Okay, so UR is r by n or r to the power n minus 1. I can write it like this, right? Integral bxr. Okay, let me write. See, yeah, you see this average, I am just writing it down, so that is why alpha n r power n minus 1, r power n is there, so that will get cancelled out, that is why r power n minus 1 is there, okay. Ball u of yt dy. Clear? Okay, sorry, Laplacian of u. Yeah, Laplacian of u. Okay, so this particular thing is there. Now you see, you multiply this r power n minus 1 here. So now that implies r power n minus 1 ur equals to 1 by n alpha n integral over bxr Laplacian of u yt dy. Clear? Okay, once that is there, now let's call this thing as, so call this thing as a equals to b. Okay, now a is r power n minus 1 ur. Okay, let's take a, therefore ar. What is ar? This is derivative of this thing. Clear? I want to find out what URR is. I am not going to directly do that. Yeah, what I am going to do is I am going to multiply it like this. Yes, so this particular term, if you just calculate this thing, what is happening? It will become n minus 1 r to the power n minus 2 ur plus r power n minus 1 ur. Clear? Rr. Okay, and now I have a URR from here. So let me write down what UR is. So specifically everything will be written down properly. R power n minus 1 URR plus 1 minus 1 by n. Okay. If you just break it up, it will become 1 by n alpha n r, okay, integral over bxr, okay, Laplacian of u yt dy. Yes, I am not doing anything but writing what ur is. See, ur, where is it ur? Ur is this, right? So I am just writing it down because of r power, you see, r power n minus 1 is already there. Okay, so that is getting converted here, and r power n minus 2 times this one, so that is why 1 by r. Clear? Okay, now we have this thing, right? Now what I am trying to say is this. See this particular thing. Now b, a is done, right? Let me do b here, so it will be better. So B, I am defining it like 1 by n alpha n, okay, integral bxr Laplacian of u yt dy. Okay, so now here I am using something called a co-area formula. Okay, so let me write down what the formula is, so it will become more easier for you to understand. If you do not know the formula, please I will ask you to look at the so this formula is essentially the polar coordinate formula. So basically co-area formula, or in some books it is also written as polar coordinate formula. Okay, very important formula. Let me write it down. So basically it says that this is not a formula. You guys already know this thing. See, if f is continuous and summable, maybe I can write it in the next page. That will be better, huh? Let me do it in the next page. It's a very important formula. You guys should know that. So let me do it in the next page. Okay, see, the formula says that this is the polar coordinate formula. Okay, so co-area, so how it's a formula to convert n-dimensional integral into integral over spheres. Okay, so now the question is this: how to convert n-dimensional integral to integral over spheres. Okay, how do you convert it? So you know this formula, right? F is from Rn to R is continuous and summable. Let's say continuous and summable. Okay, summable. Then integral over Rn, clear, f dx, that is given by 0 to infinity integral over del b x naught r f ds dr. Clear? So this holds for each point x naught in Rn. Clear? So basically what I am doing, I want to define it in, I think I discussed this thing earlier, right? So if you want to integrate f over Rn, what you do is, first of all, integrate over a sphere del b xr, and then run the radius of the sphere from 0 to infinity. You are done, right? So once you have this thing, now if you differentiate this thing, with respect to r, both sides, what happens is, so basically this is one, the second part from here only. Okay, so for the see, if you change Rn to b x naught r, let's say, okay, then this infinity gets changed to r. Okay, so in particular this is b, let's say this is x naught r, f dx. If something like this happens, then your integral becomes 0 to r. Okay, and integral del b x naught s. Okay, and f d capital S of small something, let's say fz dz, okay, and ds. Clear? So that is there. You just change Rn to b0r. So if you want to do it in a whole ball, the full ball, what you do is, you do the boundary of a small ball and then take the radius towards from 0 to infinity. Yeah, that's what. So this holds for each r positive, So now if you differentiate this thing both sides, ddr, okay, of integral b x naught r f dx, if you do that, then that will become integral del v x naught r, okay, f ds. I think this is quite clear. I'm just differentiating both sides here. So this is the important formula. Okay, so yeah, I'm going to use this formula. So I'm going to use this formula. What I'm going to do is this. See, b is what? Our b in our case is this integral Laplacian of u, right? It is, so b is 1 by n alpha n integral of del b xr Laplacian of u yt dy. Clear? Yeah. If I want to derive what br is, so b was given like this. Now what happens to br? I just this remains unchanged because that's basically a constant. With respect to r, if I am doing this integral, you see, oh sorry, this is not our del br, this is our ball, right? Over the ball. If you, I mean, by mistake I wrote it. Okay, so you see this del r of integral over f over b is the f over the boundary. Clear? So basically this is integral over del b xr, okay, Laplacian of u yt dsy. Clear? That's the only change. Okay, now what happens is, let us come back to this. Sorry, I have to write, I mean, use so many slides because the calculations are big. Okay, I mean, I have ur which looks like this. I wanted to find what urr is. I wanted to find what urr is, right? Ur is given like this. So essentially, you see, what I am doing is I am taking ur and I am differentiating both sides. I am multiplying by r power n minus 1, differentiating both sides. I have a, I have b. Yeah, now you put it together. Yes, this I want you guys to do it yourself. I mean, there is nothing to do here. Okay, once you put it together, what happens is, therefore urr. Okay, so please check this part. I mean, there is nothing to check. You just have to put I mean, interchange one line here and there. So that is equals to the average over the sphere xr Laplacian of u ds plus 1 by n minus 1 integral b xr Laplacian of u dy. Clear? Okay, so if you write it like this, then it boils down to this. This holds for any r positive. Okay, what about r equals to 0? And similarly, if you take the limit as r tends to 0 plus, of course, urr of x rt, what do you think happens? See, of course, I mean, you see this particular thing, and I mean, as r tends to 0, this thing goes to Laplacian of u. Okay, at the point x. Again, minus 1 times this particular thing, the integral also goes to Laplacian of u. Okay, yes. So basically I am left out with 1 by n Laplacian of u x comma t, right? So you remember this sort of thing we did in Laplacians also. Okay, when we did the this thing, the Laplace equation, we did this, that the average of the average of f over the ball, or over the boundary of the ball as r tends to 0 goes to f, right? F at that center of the ball. Clear? So I am using that particular trick, and then we have this thing. Yes. So now you see, so this is a formula, right? This is kind of a formula for urr. Let's call it a, I don't know, how did we call it? It is okay, 3 is there, so let's call it 4. Clear? Okay, so now you can use 4. Using 4, one can calculate u r, and then you go on doing this thing. Okay, what is going to happen then? So basically, therefore, you have capital U. You can show that this is in Cm of r plus bar times 0 infinity. Clear? Why r plus? See, r plus, of course, this is for any r positive, this is in Cm, because urr exists. Urr exists, and this is continuous function, right? So basically it is in C2. From 4 we are getting it is in C2 with respect to r. I mean, right? Okay, see URR exists, so that is why it is C2, right? Uh, Now as r tends to infinity 0 also, this is a continuous function, so basically the bar I can take it up to the boundary. Okay, so that's why using Cm of r plus bar times 0 infinity, because you can do it like this: I mean 4 times differentiable with respect to r, and then m times differentiable with respect to r, and that is why using Cm. Is it clear? I think this is quite easy. Okay, now what about UTT? Now, I mean, there is nothing much to do here. You do realize that if u of x rt is given by integral over del b x r, okay, u yt dsy, okay, therefore utt xrt, this will be given by, what do you think this is? See, if you take the t derivative here, you can just take it inside. I mean, you don't have to worry about it, because this, all of this is independent, the integrals is independent of t. So this will be xr utt of yt dsy. Clear? Okay, now what happens is, when you put all of this together, what is happening is, now therefore you see this, let's say this is 5, that's your 4, that's your 5. Now putting, see, I want to show that it solves the Euler-Poisson-Darboux equation, right? So essentially what is happening is this: utt minus urr minus n minus 1 by r ur. Okay, this is what, let us calculate what this is. See, this is utt is del b xr utt evaluated at yt dsy, okay, minus urr times this, right? So let me write it down: 1 by n minus 1 bxr Laplacian of u yt dy minus n minus 1 by r by n bxr Laplacian of u yt dy. Here, this is what we have. I'm just writing what I mean, this particular thing is urr. I'm just writing that thing. Okay, so urr is this thing. Yeah, urr is this over the ball Laplacian of u plus this particular times the Laplacian u over the bxr. Okay, so this I'm just putting all of this together, that's all. Okay, so if you calculate this thing, this r and this r is gone, right? So I am left out with this something like this: integral del b xr utt of yt dsy, okay, minus, so see this particular term, this term and this term is getting cancelled, right? This and this term is getting cancelled. Okay, if I am right, you see bxr Laplacian u, this and this is getting cancelled. Okay, so now okay, one thing I have missed, I think. See, this part I did not write: Laplacian of u over del b. So this is minus integral del b xr Laplacian of u yt dsy. Okay, now when you put it together, this term and this term is getting cancelled out, so I am only left out with this and this, the boundary terms. So minus Laplacian of u at the point yt dsy. Clear? This is what I have. Now you see, the u satisfies the problem in whole of Rn, right? So this definitely holds on the this del b xr also. So essentially this is going to be 0, and hence this thing is true. The Euler-Poisson-Darboux equation is satisfied, and also moreover, I mean, this you do not have to do anything, it's already true. That also it is clear that capital U is G and UT, that is H. Okay, I mean that is, I mean there is nothing special happening here. That is always true. So I just wrote it. Yeah, that's fine. So Euler Poisson-Darboux equation is satisfied. That's what we gather. What we are trying to do here is now try to find out the solution for the initial value problem, right? The trick here is this. So I am going to take a particular thing here. Whatever first thing first, what we are doing is this. I am going to do it for, so solution solution for n equals to 3. Okay, so as I told you, one odd thing, one is a even one. So there are two. Once we find out what Euler-Darboux equation is, now we have two options. One is to go for a odd dimension, and then after that even dimension. Odd dimension, generally speaking, if I just go directly, it is going to be complicated. Okay, so what I am going to do is, first of all, do it for n equals to 3, and then do it for n equals to 2. Yeah, then again we will do it for a general n. Clear? So for n equals to 3, this equation is called the Kirchhoff's equation. Okay, sorry, Kirchhoff's formula. Okay, I will do it later. I will specify it later. So basically n equals to 3 I am doing. And suppose U is in C2 of R3 cross 0 infinity. Clear? Okay, solves 1. 1 is the initial problem, if you remember. Okay, but in 3 dimension. Now let U and I am assuming capital U, capital G and capital H are in this kind of thing. Let me, I don't want to write it all the time. So basically, it's already defined where is capital. So 1, and let's say this is star. Okay, so 1 and star. These capital U, capital G and capital H are defined like this. Yeah, let's just assume that. Then what is happening? Okay, let capital U, G and H are defined as 1 and star respectively. Clear? Okay. Now what we do is you set, okay, U tilde to be small r times U. Yes, G tilde is small r times capital G, and H tilde is small r times capital H. Clear? Now our aim is to show that this U tilde, G tilde and H tilde is very special in the sense that UTT minus URR, sorry, not U tilde, this is becoming 0 in R plus cross 0 infinity. U tilde is equals to G tilde and UT tilde is equals to H tilde on R plus cross T equals to 0. So you remember, understood what is happening. First of all, I defined some U, G and H. With the help of U, G and H, I am defining U tilde, G tilde and H tilde. This U tilde, G tilde and H tilde solve the one-dimensional wave equation. Clear? And U tilde is 0 on R equals to 0 times 0 infinity. Now this is quite clear. U tilde is going to be 0, right? Because U tilde is given by R times U. U is a fixed number. U is a continuous function, right? Capital U is a continuous function. Okay, and so basically, bounded continuous function. So U tilde is going to be 0 in this line. It's not a issue. Okay, we just have to show this UTT tilde. U tilde satisfy the wave equation. Okay, so note that u tt tilde is r u tt. Yeah, there is nothing to do here. Why? Because u is, I mean, you understood, it depends on, I mean, there is nothing, t is not doing anything essentially here. Okay, so you can just take the derivative inside and you can just push it together. You can write see u tilde, if you are taking double derivative with respect to, what is going to happen, it r is remaining r and it is becoming capital U of tt, right? I mean, nothing changes, so you can just write it like this, and that is given by r times utt is capital U. What does it satisfy? If you remember, capital U, it satisfies the Darboux-Poisson, the Euler-Poisson-Darboux equation, right? So capital U satisfies this equation. So utt is urr plus n minus 1 by r ur, right? So one sec. It is u. So basically, it is urr plus n minus 1. N is 3 here, so it is 2 by r ur, right? Since u satisfies the Euler-Darboux-Poisson-Darboux equation. Okay, so that is there. So that is given by r capital U R R plus 2 U R, right? And once you write it down, it becomes U plus R U R with respect to R, which is U R R tilde. Clear? Clear? See, I mean, if you take u tilde, you take with respect to r, it becomes u. Okay, and again with respect to, so basically, what I'm trying to say is, when you break it in all of this up, this is basically u tilde of r, and then with respect to r is u r r tilde. This is u tilde of r, right? Okay, u tilde of r is r u r. I mean, if you derive this thing with respect to r, it is r u r plus u, right? So that is there, and that's why it is u r r tilde. Clear? I mean, this is very easy. Okay. Also, so you see, u t t tilde is u r r tilde. Okay. Now you see, g tilde of r r at the point 0, this is going to be 0. So please do it yourself. I mean, there is nothing much to do. Of course, it is 0, because as r tends to 0, g is going to 0, and r is already there. So g r r at the point 0 is going to be 0. Okay, so that is always there. So now you see, if you apply, so this is essentially, I mean, how do I put it? Okay, let me do it in the next page. Now you see, so for 0, okay, so you have to keep your patience here. This is slightly big thing to prove. That is why, okay, u tilde of x r t, this is given by half of g tilde of r plus t minus g tilde of t minus r. If you remember, the half space we did with the help of reflection method. Yeah, for r less than t, this is going to happen. See, this I mean, we showed that u tilde sorry, I showed that u tilde satisfies this equation, right? Satisfies this equation. Okay, now if u tilde satisfies this equation is in a half space. If you remember, you see, so basically I can use the reflection, right? I can use the reflection, and using reflection, now I can write down using D'Alembert's formula, that breaking up, last week what we did. Okay, if you break it up, it will look like this, and then plus half, okay, integral t minus r to t plus r h tilde of y dy. Clear? That's what we are getting. Okay, now this, see, can I write it like this? Let me write it. Now, can I write it like this? U of xt. Okay, this, can I write it like limit r tends to 0 plus capital U tilde of x r t by r. Do you think I can write it like why I can do it? See, U of xt, what is it? It is limit r tends to 0, okay, plus of course U of x r t. You remember U of x r t is the average of the on the over the sphere. Now if you take the limit as r tends to 0, what is going to happen? That average is going to convert to small u, right? So that's what I just wrote, and then I use the definition of capital U. So I mean it's there. Okay, now this is equals to limit r tends to 0 plus, this is very kind of interesting, so this is g tilde of t plus r minus g tilde of t minus r by 2r minus plus 1 by 2r integral t minus r to t plus r h tilde of y dy. Clear? So if that is the case, then what are you going to get from here? We are going to get g tilde prime of t plus h of t. Okay, sorry, h tilde of t, right? Of course g tilde and h tilde, they are differentiable functions, right? If you do that, then essentially from here what you are going to do, this is g prime at the evaluated at t, right? That's the definition, and plus here if you do it, limit r tends to 0 1, so basically you are taking the average of you see over this integral t minus r to t plus r. What is the length of the integral? 1 by 2r. So you are taking limit r tends to 0 plus 1 by 2r integral of this thing. This will actually converge to h at the center of the interval, which is t, right? So h tilde at t. Clear? Okay, so we have this. Now what we are going to do is we are going to put all of this together. Okay, so hence what you have is u of x comma t, that is, this is what can I say, u of x comma t is g prime. This prime is with respect to the t, right? Okay, so if you just put it what capital G is, it is the average of small g, right? So this is del t of t del b xt small g ds. Clear? Plus t times, because g tilde is t times g. Clear? So that is why this t is coming, and h tilde is t times integral the average x t h ds. Clear? I'm just using the definition, I'm not doing anything, I'm just using the definition. Okay, so I have this. Now, so this is your u of xt. Let me clarify this thing a little bit more. So therefore the first part, the integral del b xt, let's see what can we do with that. G of y ds of y. Okay, if you want you can write it like this. It is del b 01. I am not doing this calculation, this has been done a lot of time, you guys can handle yourself, I am quite sure. We just did it in the beginning of the class also. Okay, so this is this, yes. Therefore if you take the derivative with respect to t, so del t of integral del b xt of g of y ds of y, okay, this if you do, that is going to be integral over del b 01, okay, gradient of g x plus tz dot z dsz, right? Yes, I'm not doing anything but taking the the derivative inside, that's all. Yeah, I can take the derivative inside using chain rule. I have this, and that will give me integral del b xt, okay, gradient of g acting at y, z is y minus x by t, okay, and this is ds of y. Clear? Okay, now so once I have what this is, so essentially this particular thing I can write what u of xt is. Hence u of xt will look like integral del b xt t h of y, here, plus g of y. I am just writing everything down here, okay, plus gradient of g at the point y dot y minus x, okay, ds of y. Clear? So this holds for x in R3 and t positive. I'm not doing anything but writing this. The u of xt looks like this, right? This particular term we just calculated, and this particular term just putting it together and I'm just writing it like this. Clear? This is t times that, so that is why that t is gone. So we have this thing, this formula, this, let's call it a, capital A. So this formula, capital A, is called the Kirchhoff formula, okay. I am not quite sure about the spelling of Kirchhoff by heart. I hope that's the spelling, okay. Kirchhoff's formula for 1. Clear? Yeah, in n equals to 3. Clear? So for n equals to 3, this is the formula. Please don't write it for any dimension n. N equals to 1, we know that D'Alembert's formula, right? N equals to 2, we don't know anything right now. N equals to 3, we know that this is the formula. N equals to 2, we'll do it in the next part, okay, and then we'll do it for any n. So this is a little complicated, okay. With this we are going to end this class.